And this is the Particles Homework Booklet question 31. So we've been asked here, we've been given a graph of the maximum kinetic energy of photoelectrons against the frequency of the incident radiation. So there's the photon frequency, if you like, the light frequency. That's the photoelectrons, that's the emitted electrons, their maximum kinetic energy. Now I just want to think through this graph a little bit. If we start with our basic equation that relates to the photoelectric effect, we've got HF is phi, the work function, plus EK max, the maximum kinetic energy. HF, the photon energy. And if we rearrange that, just looking at how the graph is drawn, I've got that on my y-axis. I'm going to write that out as the subject. EK max is HF take away phi, and I can then compare that to y equals mx plus c. So EK max is on my y-axis, F is on my x-axis, and straight away that gives me that H is m, the gradient of the graph, and the y-intercept is minus phi, minus the work function. That then makes parts A and B really quite straightforward. Using data from the graph, calculate Planck's constant. So the point is that H is the gradient. There you go, H is the gradient. And then I did some calculations from some delta y's, some delta x's. So delta y, I think I went at 30 times 10 to the 14, so I read that off as 14.75, take away 0 times 10, importantly, times 10 to the minus 19 joules, got to get those powers of 10 in there when I'm reading off a graph, and then I've got 30 minus, and I read off that point as 7.3, times 10 to the 14 hertz. Just calculating that through gave me 6.5 times 10 to the minus 14. Obviously I had to get sensible read-offs. They accepted 6.6 plus or minus 0.15, so between 6.45 and 6.75. Part B was you asked to determine the maximum energy required to remove an electron from the target metal. You've got to recognise that that means the work function phi, and again from here we've got that minus phi is equal to the y-intercept. So I extended the graph here, extrapolated that graph back to a read-off, and that gave me a y-intercept of minus 5.0 times 10 to the minus 19 joules. So if minus 5 is minus 5.0 times 10 to the minus 19 joules, then phi is 5.0 times 10 to the minus 19 joules. So that was all working from that graph and using these ideas about y equals mx plus c. Then we have to explain how the photoelectric effect produces evidence which illustrates. So we've got to explain what's going on. We've got to explain that the evidence to remove those electrons is supplied by the electromagnetic radiation. And if the photon energy falls below a threshold, we get no photoelectrons. And then we get the idea of the energy only being absorbed in discrete quanta. Here are the key points, and these are probably the three I'd have gone for the 3 marks. Each photon releases 1 photoelectron. Evidence for that: increasing the intensity increases the number of electrons, not the energy of their electrons under a wave model, which is really implicitly the comparison we're going. Increasing the intensity might be expected to give the photoelectrons more energy, and that we do get electrons being released at low energies, that is at low intensities really. Probably should have had the word intensity there. Again, under a wave model, you might expect at low intensities there not to be enough energy to do that. That's really what points us towards the idea of each photon releasing 1 photoelectron. So that's the Particles Homework Booklet question 31.